modern disasters, the role of information and communication technologies, ICT, is becoming increasingly important. We see lots more people on the ground with phones, with cameras, able to really provide a picture of what's going on the ground. What you want to be able to do in these complex, uncertain, dynamic situations is pull together collections of humans with relevant software support, so relevant software agents, into a team, and that's what we call a human agent collective. And so the Orchid project is very much about the science and the engineering of human agent collectives, so how we can build them, how we can maintain them, and how we can operate them in particular scenarios. Our aim is for the Orchid project and the technologies that we develop to help first responders to make better decisions and ultimately save lives. We've looked at a number of disasters around the world. We've looked at simulations and training exercises that have been run in America and in the UK by disaster response organisations to really understand how it currently works today, what the major challenges are and how things can be made better. We've done some work with Hampshire County Council in order to be able to construct and simulate how a disaster would play out in that particular scenario. And they have a disaster response plan that they have to put in place. And one of the key challenges here was to be able to have accurate maps and simulations of how people will get out of the area.
So what you're seeing here is the map of a Foley oil refinery right next to Southampton. And as you can see on this map, there are a number of villages that contain thousands and thousands of people. So we developed simulations of pedestrians and cars moving out of these disaster areas. And using very powerful computers, we're able to scale those simulations to thousands and thousands of pedestrians and cars. In a real-world deployment of this platform, what you will have is that people will be taking pictures of the area and they will be uploading these with GPS annotations. And that will allow us to keep track of where these buildings and connections are and populate a map with all this information. We can run these simulations in faster than real time. And by doing that, we're able to estimate very accurately how many people will get onto the roads from those buildings, and therefore the congestion settings that will result during an evacuation scenario.
In a disaster, there's very little information. Typically, you may or may not know what's caused it. You may or may not know its extent. And so really there is a lack of information there. You don't know who is in the area, so what people there are around, what resources you have at your disposal to be able to understand how you can deal with this problem. In some aspects of disaster response, what you have at your disposal is an unmanned autonomous system. What we're interested in is exploring how the human first responder and these UASs can work together as a really close-knit team.
So I should bring up a terminal. In any kind of disaster, having an aerial view is really invaluable for gathering information about the situation on the ground. Whereas before this was always manned flight, now UAVs are providing this really versatile, cheap alternative for doing this. But at the moment, those kind of platforms are really labour intensive. So someone has to decide, where am I going to fly this thing? What am I going to look at next? Someone else might have to then trawl through all of that video footage in order to figure out, okay, what are the key things here that we're really interested in? So in Orchid, what we're interested in doing is supporting this and allowing more UAVs to be used by fewer people. How can we get the UAVs to decide themselves, what should I look at next given what I've seen already? So for instance, if I fly up as a UAV and have a look down, if I see something on the ground, I'm not quite sure what it is, should I take a closer look at that, or should I pass that on to a human and say, is this something that we're really interested in? Second thing is coordination. So if we have more than one UAV, how can they decide amongst themselves how to break up that task to make the best use of their combined resources? And finally is flexible autonomy. So neither the machine or the person acts in isolation. So you want to be able to make things easier for the human by letting the UAVs take control of some of the decisions, but at the same time you want the human to be able to understand those decisions and also be able to intervene in those decision processes as well. So this is the interface that Feng has developed to allow a first responder to control multiple UAVs at the same time. He can specify tasks and allow the UAVs to decide amongst themselves which ones are best to do which task. But at the same time, he can change those modifications manually if he likes. He can take control of an individual UAV and have a closer look of what it's looking at. So this really shows this idea of going from full autonomy right down to full manual control, depending on what the human thinks is most appropriate.
One of the vignettes we've looked at is Fukushima, so the recent nuclear incident. And that was very interesting. There were over 500 people who built their own radiation sensors, so they built their own Geiger counters to be able to track the amount of radiation that they had. And these were then able to be integrated with official information, coming from official sensors, in order to be able to construct a picture of what was actually going on. Now, some of the people were good at building their sensors and gave very accurate readings. Some people were less good at building their sensors, and so their readings weren't very accurate. We combined these, fused these with the official high-quality sensors in order to be able to get a much more comprehensive view of the information space.
This is a very challenging task. First, because data provided by the crowd is sparse. Second, because some reports might be untrustworthy. For example, some sensors might be malfunctioning, or some people might be reporting based on their emotional state, not the reality. So to face the challenge, what we did is to develop a novel trust-based model that allows us to learn spatiotemporal patterns that are present in the data.
The smart bit, the smart technology, is the algorithm that we constructed for putting that information together, for learning what is likely to be a good reading, what is likely to be a bad reading, and combining them in the most efficient way that we can.
During disaster response, it's very important to gather accurate information about conditions on the ground. And in order to do that, we need to motivate people to contribute this information or to verify information. So we're looking at a number of incentive mechanisms, and we are tackling this problem using lessons that we learned from a recent social experiment called the Tag Challenge. And the task there was to find a person walking around the city just based on their picture. The internet and the social media made it possible to easily invite their friends and share information, and also to track the referrals. We found 3 out of 5 people, showing that it is indeed possible. These are the kind of techniques that will help during disaster response to gather information fast and to verify it.
One of the most important things that we're interested in is studying how people actually interact with technology.
So in agile teaming, we're really interested in how we can form dynamic teams of actors so that those teams can perform tasks that none of the individuals can perform. And then we're interested in how we can disband and reform as appropriate. Within a disaster response setting, those actors may be humans and agents. They could be first responders, they could be unmanned aerial vehicles collecting imagery, they could be human analysts. We're interested in algorithmic challenges, which is really how we can calculate the best teams. We're interested in algorithms that scale, so in a disaster response setting there may be tens, thousands of actors, so how can we build algorithms that can calculate the best teaming as fast as possible? And also, how do some of the natural issues of trust and accountability within human teams, how does that impact when the teams are being formed dynamically through some sort of automated negotiation?
So, in order to build intelligent tools to support disaster relief workers, it's very crucial for us to understand how they work, how they interact, and how they collaborate with each other.
So we've designed a game to study how teams of people coordinate. Atomic Orchid is a location-based mobile game in which field responders and HQ work together to rescue as many tasks as possible before they get engulfed by a spreading radioactive cloud. The agent monitors people's locations and the targets, and on that basis can construct a plan how to optimally save the targets. So the agent forms a plan and sends messages to the players, and thereby instructs them on which targets to prioritize and who to team up with. It will suggest for you to pair up with a certain player, and it will also suggest which task to rescue to go for. What we're seeing is how the agent teams up players, sends them to certain targets, and then those targets are then being collected by the players.
We know the connection between these events, how one event connects to another. From that, graph analysis could pick up common interaction patterns, who were the key players in the game, or even the bottlenecks in an operation. Such intimate insight into what happened in an operation, I believe, would undoubtedly help disaster response planners to improve their training, improve their coordination for future operations.
As information needs to be exchanged, they need common format, a common understanding, and it's crucial to have standards for that. We have defined a standard for provenance on the web. For that, we worked with the World Wide Web Consortium, that's the body that standardizes provenance, and we are using it in the Orchid applications.
So what we'd really like is the most efficient way of dynamically mixing resources with different skills, different talents, different capabilities, and to do that continually as new tasks come along, and disbanding those teams as tasks change or new priorities come along.
One of the key tasks is to be able to make predictions, to figure out from what we've seen in the past and what we know, what's likely to happen in the future. So in particular, we've done some simulations around clouds of radiation. We've developed a range of very clever advanced machine learning, artificial intelligence techniques that will take the data for a particular place and make predictions about what's going to happen in the future.
What we want to be able to do is figure out where that cloud is actually going to be using these monitors, if you like, supplied with Geiger counters. We want to be able to determine the wind dynamics in order to be able to evacuate people from that environment in such a way that they're not subject to the radiation cloud, they're not passing through the radiation cloud. So what we're able to do is use fairly complicated mathematics to model the radiation cloud, to be able to combine observations with the radiation cloud, and also be able to generate paths through the environment which avoid that radiation cloud.
There will always be new forms of disaster, man-made and natural. And so when we have the Orchid technologies out, being used for real on a routine basis, the first responders, people on the ground, are able to understand the situation that they find themselves in, figure out what is the best thing to do, how can they best allocate the resources that they have at their disposal, respond quicker, make better decisions, and ultimately save lives.